Elvis Pillinen from the University of Eastern Finland. Please.
Hello, I'm Elvis Pillinen, and today I'm going to talk about double-slit interference with multimode null states. I'm going to thank also Andreas and Leron for helping with this work. And there's a basic outline. First, we introduce a couple concepts, then we describe how to describe coherence and polarization state of light through Stokes formalism, which allows us to describe multimode null states, double-slit interference, and because there is a change in the polarization state, there is a German phase present, which we can then connect with wave particle duality in this experiment, and then some conclusions. So, what are null states? Well, basically, null states. In null states, you have n photons entangled between two modes, and a very simple example to generate such a state for two photons is the homo-model effect, where there's a parametric delta conversion and two photons are combined with a beam splitter, which then gives two photons going either through path 1 or path 2. And this is very useful because it can give higher sensitivity for phase changes, measure phase changes. And more generally, there are multimode null states between multiple, so that there are any photons entangled between multiple different modes. So you can have n photons entangled for one, and so on. And these have applications in metrology, lithography, imaging, sensing, and so on. And now, double-slit interference. It's very important because it's one of the most important experiments in optics, and the reason being is that it's already long time ago demonstrated the wave nature of light. And in double-slit interference, you have two slits, and the light from which interferes, and you get some interference pattern. However, what has been considered more so recently is that there can be polarization modulation if vector light is used in the slits. And in quantum optics perspective, this double-slit experiment demonstrates the wave particle duality of light through complementarity. And in the recent studies where polarization modulation has been considered with vector light, it has been connected with the geometric phase in the interference plane. So, what is geometric phase? More broadly, geometric phase occurs when you have a loop in a Earth space, and it describes the difference between a global change in the system, which cannot be described solely by the local changes in the system, but there's also a geometry present. And here's a very popular illusion picture where locally the water seems to descend, however, globally there's a waterfall and water ascends, so there's some geometry present which explains this illusion. And because it's related to the property of Earth space, and Earth space are everywhere. Photons, physics, space-time is curved, etc. But now I'm focusing specifically on the geometric phase that appears when there is a polarization change, and it's because the polarization state space itself is curved, and in which the total phase between a initial and end state cannot be described simply by the phase changes in between as the state evolves to the final state. And even if there is no dynamic phase as the state evolves to the end state, even if there is no phase change in between, there can still be a total phase difference between the beginning and end states. And this kind of geometric phase is called a Pancharatnam-Berry phase polarization changes. Well, the coherence can be described between 2 points by a coherence matrix, which has factors that are known as 2-point Stokes parameters, and these are fully measurable quantities through interferometric measurements. And these four Stokes parameters of some state have corresponding Stokes operators. These Stokes operators are related to electric field operator of the system, which describes how the light field evolves to some point and is absorbed. So it's related to absorption and to signal. And the base part of this 2-point Stokes parameter describes the phase difference between one and the other point. And when we consider these 2-point Stokes parameters describe the coherence of light, but if we consider at a single point, the field, of course, it's fully coherent with itself. So in a single point, it describes the polarization properties of light at that single point. And if we consider as an example a plane wave, we get 1-point Stokes parameters. So, for example, the operator for the S0 is a sum of the number of photons in the X polarization and Y polarization, and so on. The other Stokes operators from which you can get the Stokes parameters, 1-point Stokes parameters. And the polarization state of light can be described on a of these 1-point Stokes parameters can be described on a Pointer sphere. And if the state is clear, then the polarization state is projected on the surface of the sphere, and if it's a mixed state, then inside it. And then we can use this Stokes formalism to describe the double-slit interference in the first point. So now there are 2 slits, and both of them which have polarization modes for Y polarization and X polarization. And the light from and the state of light from these slits then propagates to the observation plane where polarization modulation can be observed. Not just intensity modulation, but polarization modulation. And the electric field operator describes the system is as follows, and we can describe the Stokes parameters, which describe the coherence of light in slits, from which we can show that the coherence and slit is connected with the polarization modulation at the screen through a interference law for vectorial light. So which demonstrates that the polarization modulation does not occur only as intensity modulation, but as polarization modulation through these 4 Stokes parameters, and they are connected with the coherence between the slits. And if these Stokes parameters are considered, for example, for a if in the slits there is a coherence state, some U state, then these Stokes parameters project a circle on the Pointer sphere as the Stokes parameters evolve across the screen. And now, how do we describe the coherence and polarization state of light in the higher orders? It's a bit more complicated, but it goes quite similarly. So if we combine if we utilize the Glauber's theory of coherence, which actually was in the Nobel Prize initially, and combine it with the quantum state tomography, we can describe a higher order coherence matrix. And similarly, as in the first order case, the higher order coherence matrix is connected with higher order Stokes parameters between 2 endpoints. So it describes the coherence properties between a set of endpoints between another the first order there was only 4 Stokes parameters, but in the second order there would be 16 Stokes parameters, and in the third order 64, and so on. And these are also, at least in principle, measurable quantities, but would be more difficult. And the phase part of these 2n Stokes parameters describes the phase difference between a set of endpoints and another set of endpoints. And now similarly also there are Stokes operators for each of these Stokes parameters, and they can be shown to be connected with the Stokes operators in the first order. So if you can describe the behavior of the system in the first order, then through this you can describe the behavior in the higher order. And this is the back way to describe higher order interference laws of light. However, the general description is more complicated, so we have we are using a particular example of double-slit interference in multimode null states. So what we have now is a 4-mode null state between 2 slits and 2 polarization modes of each slit. So there are these slit modes, there are 2 of them, and both of these have polarization modes. And there are n photons entangled between each of these modes. And if we did a regular intensity polarization measurements in the first order, then if the n is larger than 1, then if we did regular intensity measurements, we wouldn't see any interference ranges. However, this 4-mode null state still does interfere, but now the interference exists in these higher order Stokes parameters. And if we use the Stokes operators for the generalized Stokes operators, then we apply them to this 4-mode null state. We can describe the coherence of the slits through only 4 Stokes operators for this multimode null state. So like similar to the first order case. And now we can describe the null state polarization modulation of light. And we find a similar result as in the first order. So there are 4 Stokes parameters which describe the polarization modulation of light for this multimode null state, which is connected with the correlation of the slits, and it's also a sinusoidal behavior, just like the first order, except that now in the cosine there is a factor of n. So in a single photon case, if there is a single cycle as you move across the screen, then in 2-photon case there would be 2 cycles, and in 3-photon case there would be 3 cycles, and so on. So the evolution is n times faster for this null state polarization modulation. And similarly, as in the first order case, we can now project the polarization state of this null state on a pointer type sphere because of this relation. And similarly, there is a circular path of a pointer type sphere as it was in the first order case. And I have created this nice animation where between the N1 and N3 cases. So here is there is a circular path as the state evolves, as the polarization state evolves across the screen. And but in the N3 case, and in the N3 case there are 3 cycles, whereas in N1 there is only 1. And the blue line describes the circular path as the state evolves, and the red line is the geodesic that connects the start and end points. And now we can begin to describe the wave particle duality. Stokes visibility, which describes the visibility of the polarization fringes, and correspondingly there is a particle information in the polarization state between the slits, which describes the particle information in polarization, and which is complementary with the intensity information. So these duality relationships connect intensity and polarization particle and wave informations together in the first order. And how do we describe the higher order case? Well, what we can do is to utilize the Null state Stokes parameters to generalize. So now you have a higher order intensity differentiability and higher order intensity visibility and so on for the polarization quantities. Right? In the case when the state is pure, then there will be an equality in these relations. And what we need these intensities and visibilities for is that they appear in the description of the geometric phase in this polarization modulation at the screen. And as I described earlier, the geometric phase is the difference between the global and local changes. So we can describe the phase changes and through the total phase difference between two points at the screen. So between this point or this point. While the local changes can be described by the total changes by small steps. And this allows us to describe the geometric phase for the in the Null state polarization modulation. And it can be seen that it can be found that it is related to half of the area enclosed to Pancharatnam-Berry sphere. So the geometric phase is equal to the half of the screen area that is covered as the state evolves. And this is solvable analytically. I don't have the full solution here, but I have, but there's a, but it can be found that the phase difference between the 2 points at the screen is related to intensity differentiability and intensity visibility, while there's a similar formula that appears as one of the dynamic phase changes. And this F function, which has a similar form to the phase difference between the points, however, is related to the Stokes differentiability instead. And this term describes the nonlinear evolution speed as the state evolves. So, as you can see in the animation, the evolution speed changes, and this is what it describes. And in the case when the polarization states in the slits are orthogonal with each other, then in that case the evolution speed would be constant. But generally that is not the case, and I haven't seen that described in other literature. And because the polarization state modulation occurs much faster, then also consequently the geometric phase also accumulates and faster. And since the non-cyclic case between two different points is more complicated, what we can do is to take the cyclic case as the state evolves to a single cycle, in which case the non-cyclic solution simplifies greatly, so that the geometric phase is described by this switchback information ratio, which is the ratio between these two types of particle information in this system. And what we can do is then to rearrange this formula a bit to show the connection between the geometric phase and wave particle duality. And so now we can describe the wave property in double-slit were able to describe the geometric phase in this multimode state interference. We were able to show that the geometric phase describes a weight property in the system, which is then connected with the rich fat information ratio, which quantifies the particle information in the system. We have shown that relationship. And finally, we have shown a framework to study higher order coherence and polarization properties more broadly. Then I would like to thank some people. Thank you.
Okay, thank you very much. We have time for some questions. Please.
Actually, we have two. The first thing which you said, if you know the first order, you know all the higher orders too. Is that true for general quantum state? I'm surprised by it. Makes it normal order.
With operators, if you can describe the first order operator, then you can, by taking the normally ordered product, you can describe the operator for higher order.
Okay, you can describe it. Okay.
Operator.
Okay. The second question is these moon states which we're using. Do you have any idea how to use them? So they're moon states with polarization. I was not quite sure if I understand which states we are talking about.
Yeah, I have seen literature. They can be generated, but it's quite difficult.
Yeah, but what is it? So it's a moon state, but then it's not standard moon state because they also have to have polarization properties, right?
Yeah, so it would be entangled between two different paths and also polarization. And I think the generation would be quite similar to homomodel effect, except that there is also some polarization beam splitters, I think.
Do you have psi minus state higher photons, or is it a bit more complicated? So if I overlap two processes with horizontal and vertical and look for higher photon numbers, that's not the state anymore. Okay, we can talk later about that.
Sorry, can you repeat that last? You said I didn't hear it, sorry.
Well, we know how to construct psi minus states.
Yeah.
Okay, you can bring up, I don't know, we don't know what's happening. These states are, of course, very much reducible. But I'm not sure if
And then
it's
you
moon
would
states
have-
in the things you want.
I think it would be the same because then you just need a path. You just make it non-collinear and you have path distinguishability and then you create.
That would be my intuition, but I'm not sure.
Yeah, I think that will be.
Then it's very easy one. Very good.
To post select.
Okay.
So, Stokes parameter, you have S1, S2, S3. One of it is 0, still you get the.
Yeah.
Right? But if geometric phase is not, doesn't exist, there's only one parameter.
Yeah, it's in the polarization modulation itself. So if you have scalar, there is no polarization state changes, so there is no geometric phase. If you have scalar, so you have to have polarization changes, and of course these changes occur in the different Stokes parameters.
And this quantified with the solid angle.
Yes.
And if we have like one of it's 0, how you define the solid angle? One of the parameters is 0.
Well, if one of them is 0, then then wouldn't you have a great circle, in which case it would be pi. Right.
Any other questions? Okay. We thank Elvis again. And now we have the coffee break. That was the last talk. We have a workshop, and we still have the discussion session after the coffee break. Do you want to say something? Add?
Maybe at the beginning of the discussion session.
Yeah, we will announce. So, for a half an hour. Coffee break.